Hello. So welcome to the quantum mechanics class. Today I will discuss one of the very important problem in quantum mechanics, particle in 1D symmetric potential well. Symmetric potential well. So I draw the potential well here. So center of this potential well at x equal to 0. Then this is the potential axis. This is the x-axis. So let's say particle is here, potential well of the mass m. It is bounded between the two infinite potential boundaries at x equal to minus a and at x equal to plus a. So width of the potential well is 2a, and potential in the both region, in this region Vx and in this region minus Vx. But Vx equal V minus x. Okay, so it means the potential is symmetric. It doesn't depend on the x values. Okay, it means we see the potential will be same in x positive region and potential is same in the x negative region. And so the boundary at x equal to a and at x equal to minus a at infinity, so the wave function will be 0 at this point and the wave function will be 0 at this point here. It means we cannot find the particle at x equal to a and at x equal to minus a and x equal to plus a. So the outside this region, definitely the wave function will be 0 because we will not find the particle here in this region. Also, we will not find the particle in this region. Okay, so outside this potential well, we will not find the particle. It means the probability of finding the particle outside this potential well region is 0. So this is the quantum particles, and the wave function associated this particle is psi x, and particle is bound to move in the x direction. Okay, so that's why we will solve only the 1D Schrodinger time independent equation. Motion is also the independent of the time. So what is the wave function for this particle? Okay, so first let's this is our objective, and for getting this wave function we have to solve the Schrodinger equation. The Schrodinger equation for this quantum particle minus h cross 2m d square psi dx square plus vx psi x equal 0. Equation number 1. Or we can write in general form dx square plus 2m h cross square e minus vx psi x equal 0. But in the region x equal to in the region minus a to plus a, the particle is free, it means potential energy of the particle is 0. Okay, so then the Schrodinger equation 2 will be plus 2m h cross square e psi x equal 0. So this is equation number 3. Now let 2m h cross square e is the k square. Okay, then equation 3 will be so this is equation number 4 here, and the solution of equation 4, general solution of this equation 4 is psi x a sin kx plus b cos kx. This is general solution of this equation, and here a and b are the constant. So we can determine these constant by using the boundary conditions. So we have the two boundary conditions here. Two boundary condition. The wave function is the 0 at x equal to minus a, and second one is psi x equal to 0 at x equal plus a. So if I use these both boundary conditions in equation 5, then so if I use this one, minus a sine minus a plus b cos k minus a. So we will get the a sine ka plus b cos ka. And the psi 1a is 0, so we will get minus a sine ka plus b cos ka. So we will get the a sine ka a plus equal b cos k. That's equation number 7. And if I use the second boundary conditions here, or I can also write in this way, plus equal 0. And if I use the second boundary condition at x equal to plus a, then I will get the a sine ka plus b cos ka, and this is 0, so k b cos ka equation number 8. So now we got two equations. One is the a sin ka plus b cos ka equal 0, and then second one is a sin ka plus b cos ka equal 0. That's equation number 9 and equation number 10 here. So if I add 9 and 10, then what I will get? I will get 2b cos ka equal 0. Or I can write b cos ka equal 0. That's equation number 11. And now if I subtract 9 to 10, okay, equation 9, so we will get, and writing here, I will get a sin ka equal 0. So if I write these both equations here again, it means a sin ka equal 0, and then b cos ka equal 0. So let take a equal 0 and b equal 0. If I take a equal to 0 and b equal to 0, then I will get a sin k equal 0 and then b cos k equal to 0. But if I consider a and b both are 0, then here the wave function will be a cos kx. So if the a and b 0, it means psi x equal 0. So psi x 0 means no particle inside the box. But this is not a case. The particle is inside the potential well. It means the psi x will be non-zero for any k value inside the potential well. Then consider second case. Let's take sin k equal 0 and cos ka equal 0. So in this case, I will get the a sin k equal 0 and then b cos k equal 0. If I consider sin k equal 0 and cos ka equal 0. So if I consider, then what I will get? I will get sin, the wave function will be constant for given k values. So for given k values, when we put the value of the sine and cos k, we will get the what is the k value here from the both cases, and then we use that k value in the general solution psi x, and the psi x will be constant. Okay, but this is not a again the case. It means we cannot take the a and b equal 0 or sin k a and cos k equal 0 simultaneously. So we can consider the alternative case. Then we have two options. First one is if a equal 0, then cos ka equal 0. Then second is the b equal 0 and sin ka equal 0. So if I consider these case, then I will also get both the equations. Both condition will satisfy here. This equation 13. Okay. So now if I consider one case here first, then we'll try to obtain the value of the k and then the constant a and b. So let's take the case first. It means b equal 0 and then sine, so let's say a equal 0 and then cos ka equal 0. So if I consider this first case, then so if cos k equal 0 means the k value should be very the integer of the pi by 2. Okay, and the n should be 1 3 5 7 like this. So from this I will get value of the k and pi 2a. Let's see equation number 14 here. And a equal 0, so the solution psi x a sin k, so a will be 0, so we will get only the b cos kx, and if I use the value of the k here, k is the n pi 2a x. So this is the getting the general solution here, because n pi x divided by 2a. So now what is this constant b? So I can use the normalized condition to get the constant b. So probability of finding the particle between both boundaries, it means x equal to minus a to x equal to plus a, always 1. So if I use this wave function here, then n pi x divided by 2a, then b cos n pi x divided 2a dx, b square minus a plus a, then cos square dx, then minus a to plus a, 1 plus cos 2n pi x divided by 2a dx 2. Okay, so after solving this integral, I will get, so this is equal to 1. Okay, so I will get b square equal 1 by a, and then I will get b equal to root 1 by a. So this is the coefficient b here, and if I use this b in the equation 15, so the solution psi x will be root 1 by a cos and pi x divided 2a. Now if I consider the case 2, means if the b equal 0 and then sine ka equal 0. So sine ka equal 0 means ka should be n pi. Let's take the n prime pi here. And so k is the n prime pi a. And here n prime is the 1, 2, 3, 4 integer. Or I can write, if I multiply this and divide by the 2, then I will get this one. And then I can write also n pi here, and here n equal to 2n prime. So if use the value of the n prime, then I will get the value of the n will be 2, then 4, 6, 8, like this. Okay, so k value will be n pi divide 2a, and n 2, 4, 6, 8, 10, even number. So if I use this k value, and then the solution psi x a sine kx plus b is already 0, so second term will be 0, and then we will get a, and then k value is the n pi divided by a x. Now we have to calculate the value of the a, constant a, then we'll again use the normalized condition. And minus a to a psi star psi dx 1, and then I put the value of this one, so I will get the a square sine square and pi x divided by 2a and dx. Okay, so after solving this one, if I solve this, after solving this integral, I will get, after solving this integral, I will get the value of the a is the 1 over root a. Okay, so now we can put the value of this a in equation 17. Equation 17, we get psi x root a sine n pi x divide 2a. n equal 2, 4, 6, 8. So now we are getting the two solutions. One is the psi x root a cos, and second one is the for this n is the 1, 3, 5, 7. This n equal 2, 4, 6. These are the two solutions. Then what is the energy eigenvalue? So we know that the k value is the n pi divided by a for all n. For all n, it means n equal to 1, 2, 3, 4. So from this we can write, and then we know that the k square, if I square on both sides, then k square is the 2me h cross square. Then it is equal to 4a square, and from this we will get the en equal n square pi square h cross square 8m a square, n equal to 1, 2, 3, 4. So this is the eigenvalue of the nth state. So this energy level will be the ground state, and then is proportional to n square. Then this is the 4 times E1. Then this will be the 9 times of the E1 and 16 times of the E1. Okay, it means discrete values of energy. And we also so the Eigen function, you already derived this one. For n equal to 1, 3, 5. So if replace x to minus x, then psi x will be psi minus x for this function. Okay, it means the sin x is even function, and root a sin n pi x divided by 2a for n equal to 2, 4, 6, 8 even number. Then psi x will be not equal to minus sin x. It means if I use the x equal to minus, then sine function will be minus sin x. So I will get the 4 for this function. Okay, it means the sin x root 1 by a sin n pi x 2a is the odd function. Okay, so we are getting the even and the odd function for this particular case. So if I plot the graph, this wave function, minus a plus a, and that's x equal to 0. Let's say this is the ground state. This is the n equal to 2. This is the n equal to 1. And then this is the n equal to 3. So this is psi 1x is the 1 over root a cos pi x divided by 2a. And for this is psi 2x and 1 over root a sin 2 pi x divided 2a. Similarly, this psi 3 will be 1 over root a and cos 3 pi x divided 2a. Okay, similarly we can plot the other functions for the different n values. It means for n equal to 1, the wave function will be even function. For n equal to 2, wave function is the odd function. N equal to 3, even or even. Okay, so for n equal to 1, 3, 5, 7, solution will be even function. And for 2, 4, 6, 8, solution will be odd function. So by using this wave function, we can get the probability distribution of the particle in the different energy levels. Now again the question is here that why we are not taking the n equal to 0? Because if I consider the n equal to 0, then the wave function, if I take the both solutions, even or odd solution, then I will get the constant wave function. And then this will be 0. Okay, so